So the last part of this unit, we are going to have a big chat about a branch called mechanics. Essentially, we're going to be looking a lot at energy. So the big things we're going to be looking at: mechanical energy, conservation of mechanical energy, the work energy theorem, isolated systems, and power. So conservation of energy is going to be the big overarching theme of this part of the unit. A lot of what you're going to see here is Science 10 or extensions of Science 10. So there should be a good degree of familiarity with what we're going to be talking about for the next little bit. So on that note, let's talk about the first topic and something that you have seen in Science 10. So you have seen work. And work is one of those things we got to be a little bit careful with because, we have terms that we use in physics. We also use those same terms in everyday life, and sometimes they have different meaning. For us in everyday life, we kind of take work to mean like effort, and that's great, but that's not quite the case in physics. So in physics, work has a very formal definition. It's a measure of the amount of energy that's transferred when a force acts over a given distance. So if I apply a force and move something, I'm doing work on that object. So the key components to have work in physics: you need a force and you need a displacement. And then to add a caveat to that, you need some component of the force to be in that direction of the displacement, which we are going to get soon. So mathematically, the work is going to be the force times the distance times the cosine of the angle. Now, you've probably seen in Science 10, W equals FD. That is basically comes from this. That's the case when theta equals 0. The angle here measures the angle between the force and the displacement vectors. In Science 10, you assume that they were in the same direction, so this breaks down to W equals FD, and most of what you'll do in Physics 20 is going to break down to W equals FD anyways. This is just how the equation is presented on the data sheet. So W is our work in joules, F is the magnitude of the force that's acting on the object, or the force acting on, basically it's the force that's involved. D is going to be the magnitude of the displacement. And like I said, theta is that angle between the force and displacement vectors in degrees. We'll see some examples of that. And yeah, just as a reminder, for the most part, we have theta equals 0, so F, in this case, force is going to be parallel with displacement. So when we have that case, the equation just works out to W equals FD. So you're really only going to be using this when there's angles involved. A lot of times, though, W equals FD is going to be more than sufficient. Now, we've introduced a unit that you have also seen in Science 10. So the Joule, named, probably not surprisingly, after a gentleman named James Prescott Joule. So in fundamental units, if we were to break the Joule down, 1 joule is a kilogram multiplied by a meter squared divided by a second squared. Not fundamental, but helpful as well. Sometimes it's easy for people to remember a joule is a Newton times a meter. But this is the fundamental definition of the Joule. And yeah, let me remind you, for our equation for work, we have to have 2 important points that we want to consider. So we only want, first of all, the component of the force that is parallel to the displacement, or, anti-parallel. We want some component that's in kind of the same plane. And in Science 10, that was always the case. And for work to occur, there has to be a non-zero displacement. So if you're applying a force on something, that object has to move. If it doesn't move, you're not actually doing work on the object. So let's look at some simple examples of this. So we lift a 20 kilogram box of, in this case, I guess memes, off the ground to a height of 1.45 meters. We want to determine the work done against the force of gravity. The other thing you're going to see with work is something in physics where we're really careful with the language. We'll usually be talking about the work done on something, the work done against something. So in this case, we're identifying the work that we're doing against a particular force. We have to overcome the force of gravity. Now, we know that work is just going to be Fd cos theta. But in this case, since we're going to be lifting something up off the ground, we're lifting something up off the ground, and the force, and we're doing that work against the force of gravity. So the force we're applying is going up, and the displacement is also going to be going up. So in this case, theta is going to be 0. Work is just actually going to be Fd. And as I mentioned, you might as well just start with work equals Fd. Don't put the cos theta term in unless there's like an explicit angle mentioned. Now, in terms of the force, we would like to work against the force of gravity. So what we're going to have here is, instead of F, we're going to have the force of gravity, which we know is just mg. And then we can multiply that by d. So we know the mass, we know the acceleration due to gravity, we know d. Keep in mind, for all of this stuff here, don't worry too much about direction right now. This work is a scalar. The signs I will talk about in a little bit, because we do have to worry about it, but you don't have to worry about the sign of g and like being 9.81 or negative 9.81. We're just going to put it in default as positive 9.81. So we have the mass, we have g, we have our 1.45 meters. So for this, we are going to get about 284 joules. So what this is telling somebody is, if you want to lift something up against the force of gravity and you want to lift it up 1.45 meters, you will need to put in 284 joules of work in order to accomplish that goal. Now, suppose we want to walk this box a horizontal distance of 20 meters at constant velocity. So we want to find the work done by walking the box. So we're going to go with W equals FD. Again, we're not looking at angles because nothing's been mentioned. Now, in the direction of walking the box, we also see that we have constant velocity. Constant velocity tells us that the acceleration is 0. That's also going to tell us that the net force is 0. So if the net force is 0 on this thing, we're actually going to get the work done is equal to 0. So keep in mind, for work questions, watch out for something like constant velocity. Sometimes we throw that in there to kind of trick and trap you, so be really careful with that. But like I said, when we're doing work problems, pay attention to the wording, because usually it will give you an indication of what force you have to consider. Like if you're working against the force of gravity, working against the force of the spring. So usually when we're, as I said, when we're doing work, we'll tell you we're either doing work on something or work is being done by something. And that leads me into kind of this last little distinction here. I mentioned that work is a scalar, and usually for scalars we just deal with positive values. Work is kind of a little bit of a special thing. It's made up, to calculate work we use vector quantities to get something that's scalar. But the thing is, this time though, we have to actually be mindful of the signs. So this scalar quantity can be positive and it can be negative. What those positive and negatives mean depends on what's going on. If we have positive work, we would say that the displacement and the force, they're acting in the same direction, and we're going to say that energy is added to the object. So energy is transformed into that system. And then this force is going to be used to increase the object's speed. So if I push on a box and make it move, if I apply work on that box, I'm going to be doing positive work because I'm going to increase the box's speed. Now, we can also have negative work. Something like the force of friction is going to do negative work. Usually the displacement and the forces are going to act in opposite directions. So like for example, if I push on a box, if I have an applied force that's going this way, force of friction is going to oppose that. So I'm going to have an FF this way. So my displacement is going right, but my force of friction is going left. If we were to say, what is the determine the work done by the applied force, that's positive work because that's energy that's going into the box to move it. If I said determine the work done by friction, well, the work done by friction is going to be negative because it's opposing the motion, it's opposing what we're doing, so we have to account for that with our sign. So when we have negative work, energy is going to be removed from the object, and that force is generally going to be used to decrease the object's speed, which we know with friction. Friction generally tries to slow down the motion, it's going to oppose it. So that's where we want to be mindful with the signs. And when we refer to positive work, it's generally work being done by the surroundings onto an object. So if you have a box and you start to push it, you are part of the surroundings. You doing that work on the box is positive work. When we deal about negative work, that's usually done by an object onto the surroundings. So when we're dealing with the force of friction, we're talking about the box kind of doing work on everything around it. And basically that's where that friction comes from, and that's going to give off heat. The positive, negative sign of work, the whole doing work on an object versus work being done by an object, that's a distinction we'll work on more in Physics 30, and that's something you work on extensively at post-secondary physics. Especially if you do any courses with thermodynamics and you start to look at gases, that becomes significantly more important. So let's look at an example here. So we have net work is done by friction to change the velocity of an 8 kilogram wagon as it moves along a horizontal sidewalk at 15 meters per second. So we have a 60 Newton frictional force opposite to the wagon's direction of motion. Brings it to rest in 2 seconds. We want to determine the work done on the wagon by this frictional force. Alright, so here's our lovely little wagon here. This is great. So we're going to say that the wagon is traveling this way. So that's its direction, and I'm also going to call that direction positive. Now, friction is going to act opposite to that wagon's direction of motion. So we know that the force of friction is going to go left, which means that we also know it's going to be negative. So for us, based on this force of friction being 60 newtons, we could actually say that it's negative 60 newtons, just because that negative is opposite to our positive convention. We know the mass is 8 kilograms, and we know that the initial speed is 15 meters per second. We're told it's going to come to rest, so VF0, and we have a time of 2 seconds. So we would like to determine the work done by the force of friction. Now, we know that work is just going to be FD, or in this case, since we want the work because of friction, we're going to use the force of friction here. We have that. What we don't have is the distance though, but we can certainly determine that because we know VI, VF, and T. We can use this to find distance because I know that initial speed, I know the final speed, I know T. We have an equation that's going to help us out here. It's an equation that we actually really have not used extensively in the course, but it is going to help us out in this case. So I know that D, according to my formula sheet, D is VI plus VF divided by 2 multiplied by T. So that is what we are going to use to solve for this distance, because we want to find out over what distance this force of friction actually acted to stop this wagon. So I have this VI of 15 meters per second. We're going to add to it nothing because it's coming to rest. Divide that by 2, and we're going to multiply that by a time of 2 seconds. So 15 divided by 2 is 7.5 times 2 is 15. So what that's telling us is that based on the information that we have, the distance, based on this object starting at 15 meters per second and stopping in 2 seconds, it must have covered a distance of 15 meters. So with that, what we'd like to do is we'd like to use that to find the work done to friction, due to friction. So we know that the force of friction is negative 60 newtons, and we know it's acting at a distance of 15 meters. So what we're going to get is we're going to get that the work due to friction is negative 900 joules. So the negative is just telling us that energy leaves the wagon, and also wagon slows down. So this is an expected result. If we have friction, we should absolutely expect the work done to be negative. Now I only have 2 significant digits, so I guess I should say the work done due to friction is negative 9.0 times 10 squared joules, or you could put negative 0.90 kilojoules. But yeah, that's all we're doing for the work here. So we found the force of friction, or we were given the force of friction, and we just need to find the distance of which that force of friction actually acted. Don't worry too much about the positive negative aspect of work right now. We will explore it in more detail later. This is just to kind of introduce you to work in general.